So today we're going to move on to the next section, and the next section is titled LU decomposition or factorization. And what we'll do is we'll take a look at an example and do what we did last time, which is to try to find the inverse by doing elementary matrices. And I might need some help using Mathematica or something to help us find things a little quicker. We'll see how quickly we could do it. But what we'll do is we'll start off with this 3, 4. So we're this chapter has how many? How many sections? 7. So these sections are fairly involved, and so we're taking a while to complete one chapter, and then I don't remember if the next exam is going to cover 1 or 2 chapters. I think we covered 1 and 2, right? Chapters 1 and 2. So. No, we're on 3 right now. Yeah, your differential equations is different. Yeah, so differential equations, we're moving a little bit faster there, but that's really the speed of the sections. And these sections are quite long and involved. Yeah, but it still moves a little faster than this. All right, in any case, we are in whatever section we are. 3, 4, the LU decomposition. So, like I said, what we'll do is we'll row reduce this to get it to. We won't go all the way to the inverse, but we'll at least row reduce it to see how what we'll get out of this. And then what we'll do is we'll set up a matrix equation, an equation with matrices. We'll call it E1, E2, E3, and A. We'll call this one A. And then we'll see what kinds of interesting kinds of matrices will come out of this. All right. So I'll probably leave the first row alone, and I'll multiply. I guess I don't have to multiply it by anything. I'll take row 1 and add it to row 2. So this wasn't the exact same notation I used earlier, right? I say row 1, row 2, replace row 2 or something like that. Or I might have even written it backwards. So this is how I'm most comfortable with. So I'll do it like this. What does it imply? It implies that this is the row that doesn't change. This is the row that will change. And I don't know if that helps. That's what that says. Okay. No change. And then change. That says change. Okay, it says change. Trust me. All right, so I'll have the first row not change. That's 2, 1, negative 2. And then the second row will change, and I'll get a 0 for that one. And I'm just adding, so I'm not multiplying by anything. So this will be a 4, and this will be a negative 6. And then since I have room over here, I can do this in another step as well. So I'll do this in the same step. This time I'll need to multiply by negative 2. I'll take row 1 and multiply that by negative 2, and I'll add it to row 3. So this would be negative 4, positive 4 is 0, negative 2, minus 3 is negative 5, positive 4, and 0 is positive 4. Okay. So I'm looking at this negative 5 now and want to get rid of that. So let's see if we can get rid of that. What? 5 over 1? Oh, 5 row 1. Yeah, I would probably want to do something with row 2 instead, because there's zeros here, and I don't want to change this from anything else because I want to keep it at 0. So I'll take row 2. What do I need to do row 2? By what? Well, this is 4 and this is 5. I want it to be 0. 0, 4, negative 6. 5/4? Positive or negative? So positive 5/4. So positive 5/4 would give me positive 5. That would be 0. Positive 5/4 here would give me something else. I have to write it down. I forgot what I'm going to write down now. 15. Negative 14/4. Negative 7/4. Is that right? Or is it 7/2? Oh, is that good? Yeah. Boy, that was uncomfortable. Okay. Do we need to close that? All right. So how many row operations did we do to get to this point? We did 3 row operations, right? So row operation, what was the first row operation that we did? Let's call it E1. What was the first row operation that we did? We did R1 plus R2, right? So we took, let's put an identity matrix off to the side here. And let's do R1 plus R2 on that. And so our elementary matrix is going to be what? 1, 0, 0. And you add it to, you add R1 and R2, you get 1, and then 1, 0, 0, 0, 1. So that's our first elementary matrix. Is that good? Yeah? Let's take our second elementary matrix. What was the second thing that we did? Negative 2 times R1 plus R3, right? So how's that going to look like? So R1 doesn't change, R2 doesn't change, and then I took negative 1 or negative 2 times the first row, added it to the third row. 1. Okay? And then the last one, what was the last one that we did? So, oh, there's a 5/4 in there. So 5/4 row 2 plus row 3. Okay? Okay. Yeah. Is that what I want to do? Let's see. Oh, let's see. We'll do that later. Lower triangular. Oh, are you reading ahead? Okay, so this 3.4 is called the LU decomposition, and L stands for lower triangular and U stands for upper triangular. Now, there's some interesting things that are happening here already in terms of L and U, in terms of lower triangular and upper triangular. And if you take a quick look at a result after doing these three basic row operations, elementary row operations, we have, what can you say about this matrix? It's an upper triangular matrix, right? Now, what can you say about the elementary matrices that we have so far? They're all lower triangular, right? So you think, aha. Now, there's a theorem that we're not going to prove that says that if you multiply two lower triangular matrices, you get also a lower triangular matrix. We kind of struggled through a proof of multiplying two upper triangular matrices, and we said that the product of two upper triangular matrices is an upper triangular matrix. So the same business for lower triangular matrices. A triangular matrix, an upper triangular, says that zeros on the lower part and non-zeros on the upper part. A lower triangular matrix is non-zero. The lower or upper refers to the non-zero portion of it. So the lower triangular matrix is this. So before I come up with the LU business, it's not quite complete yet. Let's take a look at, let's see if we can complete this picture a little bit better. So far, this is what we have. We have A, that's our matrix. And if we apply A to E1, it's a matrix multiplication. In fact, I'd like to do this by hand, but it's going to take a little bit more time. So I'm going to use Mathematica to help me with some of this stuff. So let's first define our A. I don't know.
You can get a different matrix if you.
So we didn't put it in a row actually.
Yeah, we just did.
Right, we didn't finish the row, the reduced row echelon form.
So it could be different numbers.
It could be, maybe.
No matter what, it's still multiplied to the same number.
Right. You should get the same. So, right.
So E2 is equal to 1, 0, 0, 0, 1, 0, and minus 2, 0, 1, and E3 equals to 1, 0, 0, 0, 1, 0, 0, 5/4, and 1. Okay, so let me first take a look at E1 times A. So E1 times A is wait. 0, 0, 0, 1. Four, 4, 3, 0. No. Yeah, I just wanted to multiply E1 times A. This is E1. No. Oh, I have to do dot. No, okay. Is this what we expected?
Yes.
What if we did E2 dot E1 dot A? Okay. So yeah, we did 2 steps on this matrix, but if we take a look at the first step over here and we didn't change the last row, then we got essentially that first matrix applied, or the first elementary matrix applied to A. And then now if we take that last one where we have E3, E2, E1, multiply with A, then we get our resulting matrix. So, just wanted to show that. So far what we have is that if we apply these elementary matrices to our original matrix A, we're going to get our upper triangular matrix. And then we've already made the observation that E1, E2, and E3 seem to all be lower triangular matrices, right? But we want that to go on the other side. So remember, if we want A to get A by itself, what we need to do is we need to kind of do the inverse one by one or piece by piece. Or if we want to grab this whole product of matrices and we take the inverse of that, the inverse of a product is the product of the inverses in reverse order. E1 inverse, E2 inverse. So if we do our matrix algebra on this by taking the inverse or by solving for A, what we have is a product of inverses of lower triangular matrices. Now, we probably should also prove that an inverse of a lower triangular matrix is lower triangular. Or is it? Yeah?
So those go in front of the U?
So they would go in front of the U. They would go to the left of the U because I would undo it one by one here, or I would take the inverse of both sides. On the left side, you would take the inverse on the left side, so the inverse would be on the left side. Left side, yeah, left side. U is this upper triangular matrix that we just found. And so what we're interested in now is figuring out what this is equal to, and we'll see that this is actually going to equal to a lower triangular matrix. And remember the inverses, I think they were easy to find, or at least they were yesterday or Monday. Or were they easy to find? I don't know. I forgot.
So for the first part, when you're multiplying the elementary matrices times A, why do you do it in reverse order in the way we did it, like by hand?
because we're doing, this is the matrix that we have, right? And this is the first operation that we made. So what we need to do is we need to apply this elementary matrix on A on the left side. After that, we're going to get a result for this, and then we're going to apply this as our second step. And so our second step, which is E2, is going to be applied to our resulting matrix here. And then, and so on. All right. So let's take a look at the inverses of these things. I mean, we should. But what if we just say they're lower triangular and they're okay? Okay, let's take a look at them. How would we deal with E1 inverse? Or what? How would we get E1 inverse? Should I do this in this color? What is E1 inverse supposed to look like? Is that room? Ah. Anybody? Huh? So remember that the inverse of an elementary matrix is another elementary matrix of the same form, except there might be some slight changes, right? Does that make sense? Roman's just laughing. It's the same but different, right? So it's the same form, except if we want to undo something, we need to change. There's one little slight bit of change in it. And the change for a multiplying a row by something and adding it to another row is just multiplying it by the opposite sign and adding it to another row. And so that's really what's happening here. To take that inverse, this is what we would get. It would be, no, what's the last row? Positive 2, yeah, that. So to get E2 inverse, it's essentially the same thing, except instead of negative 2, that move that we made over here, we're going to look at the positive 2, 0, 1. Why? Because if we multiply these two together, we should get the identity matrix. And what we're doing is we're essentially undoing what this elementary matrix did. The elementary matrix multiplied row 1 by negative 2 and added to row 3. To undo that, I would multiply this by positive 2 and then add it to row 3. So this type of elementary row operation is really just taking the opposite sign. In fact, we have notes on this the other day where we took a look at the 3 elementary row operation. Now, granted, we're just dealing with one elementary row operation here right now. So what would this one be? Negative 5/4 and 1. Okay. So they're still lower triangular. Okay, so that's still good news. Now the last thing we want to show is that when we multiply all these together, which is what we want to do, we should still get a lower triangular matrix. And we already know that because the product of 2 lower triangular matrices is lower triangular. So let's actually multiply it out. This one, I think I'll just have, well, actually, it might be good to multiply it out by hand. I don't want to. All right, we'll do it. So there's 3 of them, so we have to do 2 at a time. Let's take a look at E1 inverse and E2 inverse. So E1 inverse, E2 inverse in that order. I'll take the first row, and the first column would be 1. The first row, second column would be 0. The first row, third column would be 0. Second row of E1 and first column, that's -1, 0, 0, -1. Second row, second column is 1. Second row, third column of the other one is 0. And then third row, first column, third row, first column is 2. Third row, second column is 0. Third row, third column is 1. You see anything interesting in your result when you combine E1 and E2? Yeah. Right? Do you guys see it? You guys see what Federico saw? Yes. Yeah. So the last one, if we multiply this by E3 inverse, we should get that spot where -5/4 is sitting to be -5/4 there. Pretty interesting, huh? Let's actually show it. So this is E1 inverse, E2 inverse, which we already got. And now we're going to multiply that by E3 inverse. And we'll see that this is going to be my first matrix times my second matrix. So first row, first column is 1. First row, second column is 0, and etc. The first row, the second row, first column is -1. And why don't I just fill in the rest? All right, the third row, first column is 2. The third row, second column is -5/4. And the third row, third column is 1. So, if we imagine that we started off with an identity matrix with 1s in the diagonal, 0s on the upper and lower sides, and then we just took a look at what happened here in the lower triangular portion, what we get are exactly, well, not the original row operation that we did, but the opposite of the row operations that we did. In that spot, we got a -1. In this spot, we got a +2. And in this spot, we got a -5/4. We essentially filled in those places where we would have had zeros from the identity, and now we filled in with those numbers. So this turns out to be a lower triangular matrix. Not only that, it's a lower triangular matrix with 1s in the diagonal. It's actually called a unit, lower unit, or unit lower triangular unit. Unit lower triangular. It's in the book, so we'll take a look at it in a minute. In any case, this is what I wanted to say. We get 1, 0, 0, -1, 1, 0, 2, -5/4, 1. times the upper triangular that we got in the beginning, 2, negative 1, or 2, 1, negative 2, 0, 4, negative 6, and 0, 0, negative 7 halves. So that is our matrix. A can be broken up into a lower triangular and an upper triangular matrix.
So then you were pointing out that this scheme where L, you don't really have to calculate. You can just kind of write in the
Yeah.
value. It only works if you're very disciplined about how you make U. If you just decide to do something anyway, if you don't do things in the right order, it's going to work.
Yeah. So what Hal is trying to say is that if you go through the row reduction to make this into an upper triangular matrix, which is half of our task here, right? We want an L and a U. But if we go through these steps to get U, then we have one of the two matrices that we need. Now, to get your second matrix, the L matrix, instead of doing all that stuff that we did with the elementary matrices and doing all this business over here, if you just look at the values that you get when you do your operations to get your row echelon form, you see these numbers over here. These are the coefficients of things that you're multiplying. Those, or the opposite of those, will become the same coefficients, oops, down here, the same coefficients that you would get for the lower triangular part of your matrix. Okay, we'll do another example where we're going to focus on just doing the, quote, shortcut method of doing things. Okay. But there is some discipline part over here where you gotta, one, keep track of things, and then two, there's three elementary row operations. We only did one type of elementary row operations. There's one more type that's legal, and that is when you multiply a row by a scalar, and that's okay for this process. What was the other? There's three elementary row operations. What's the third one? The third one is swapping rows. If you swap rows, then this process is going to fall apart. Okay? So swapping rows will not be permitted just yet, but we're going to have a workaround that. We're going to allow for a swap in the beginning if that's going to be something that's necessary for us. Okay? All right. Let's go to my notes here. So I kind of started with an example instead of throwing out the definitions and stuff. So this is the definition. A square matrix is called upper triangular if all its entries below the diagonal are 0, and the upper part of the diagonal is non-zero. And it's unit lower triangular, so the unit comes first. Unit lower triangular if the entries in the diagonals are 1 and everything else above it is 0 and everything below may or may not be 0, but in general non-zero. So an LU factorization is where we can take a matrix A and factor it into a unit lower triangular times an upper triangular matrix. Okay? So, any questions so far?
Do you want to do that in 3 steps? So like we don't want more than 3 operations
If you have a 3 by 3 matrix, yeah, probably.
based on the size.
The size of the matrix, yeah. So here are a couple theorems that we're not going to prove. A square matrix can be, if a square matrix can be reduced in row echelon form without any row interchanges, that's the row swapping elementary matrix or elementary row operation that we tried to avoid, then you have an LU factorization. And if it's necessary that you have to swap at some point, then again we'll have a work around that where we'll allow for that swapping to happen in the beginning before we start doing our row reducing. What else? Uniqueness. I need to. Little squiggly lines are annoying. So if it's invertible, then the LU factorization is unique. So the question about that, Becca, about if there's more than one way to do this, well, the point is that the L is actually not just an L, it's a unit lower triangular matrix. So to ensure that it's a lower unit triangular matrix, it should be unique. So the only way where it might not, your row reduction might not be unique is that when you row swap. And when you row swap, then things change a little bit. We'll talk about permutations in a minute. Okay, so this is a bunch of basic theory on this LU factorization. And so what is it good for? I don't know. Just for fun. You know, they kind of equate it to like factoring. If you have 15, what's the use of writing 15 as 3 times 5, right? I don't know. Well, an LU factorization, if you have huge matrices, 10 by 10, 100 by 100, then LU factorization, if that's an easy step to take, it might be good to have an LU factorization to be able to solve a system of linear equations. So that's one of the basic motivations that they give in doing this. So let's keep working on the same matrix A. What do I want? I want the book. I actually stole A from one of these things. So what they have here is they have a system A, x is equal to b. System of linear equations, and what they want us to do is to use the LU factorization to solve for this instead of trying to solve for instead of trying to solve for it directly. Let's use this this factorization to see if we can simplify our work a little bit. So the idea here is that this is your L, and this is your U, and this is your matrix A. So L times U is our matrix. So what they're saying here is that A x is equal to, and then your b is negative 3, 1, 0. So what they want us to do is they want us to solve for x. And the way we're going to try to solve for x is to take it in 2 steps. Because A is not in any lower or upper triangular form, what we're going to do is instead we're going to write A as L times U. Okay? So we're going to try to solve for this. Oh, how are we going to solve for this? I forgot.
So you can solve ux equals b, right, by reverse substitution.
Yeah,
And then you,
and then do the L.
the point is they're both, you never have to calculate any inverses because they're both triangular and therefore either
Right.
backward substitution or forward substitution that you just kind of, calculate the answer.
So if you take ux equals b, what we're going to come up here with is another vector, and then we're going to from there solve for the rest of them. Except we don't want to call it x, do we? I think they call it y in the book. So what do they have in the book? Y equals what? Let me see. This is our book?
That's the third version. It's really old.
Oh, okay. All right. So here's what they do. Sorry. So it turns out that u times x is going to be another vector. So this is the vector that they're going to call y. And then they're going to have L times y is equal to your b vector, minus 3, 1, 0. So L is equal to this, 1, 0, 0, negative 1, 1, 0, 2, minus 5/4, 1. And then times some unknown y vector, is equal to minus 3, 1, and 0. So if we kind of list this out, we're going to get y1 is equal to, or y1 plus 0 is equal to negative 3. So we got a value for y1. And then we're going to get y2, negative y1 plus y2 is equal to 1. So if y1 was equal to negative 3, what's y2 going to equal to? Minus 2? Yeah? And then we have 2y1 minus 5/4 y2 plus y3, and that's supposed to equal to 0. So we have values for y1, y2 already, so we'll put that in. And this is the back substitution business that's happening. So this would be negative 6 minus plus 5/2 plus y3. So y3 is equal to 7 halves. Right? So those are the y values, and then to get the x values, you have to say, well, ux, you let ux equal to y, which you just found, right? So u was 2, 1, minus 2, 0, 4, negative 6, 0, 0, negative 7 halves. X is your unknown at this point. And the y that you just got is going to be your y vector, minus 3, negative 2, 7 halves. So because it is triangular, it's still going to be another back substitution process, but a lot easier than having to find inverses or row reducing. So we have the bottom row is going to be negative 7 halves, x3 is equal to 7 halves. So that gives x3 is equal to negative 1. So we have 4 x2 minus 6x3 is equal to negative 2. Is this making sense? Is this, we're back solving now. So we came up with an equation with Ly is equal to b, and then we found y equals what y is equal to. And since we replace ux with y, we're going to solve that ux is equal to y. And then we got u times our unknown x is equal to, before unknown, now known y vector. And then that's another back solving substitution. So x3 is equal to negative 1. This says that 4x2 plus 6 is equal to negative 2. So subtract, negative 8, divide, negative 2. So x2 is equal to negative 2. Is that correct? And then finally, we got 2x1 minus x2 minus 2x3 is equal to negative 3. And then you put in the values for x2 and x3. So x2 is negative 2, x3 is negative 1, and then whatever this turns out to be. Positive, 4, 7, negative 7 halves. This is x1, sorry. So x1 equals negative 7 halves. U was the matrix, the upper triangular matrix up here. And then L is the lower triangular. So this should have been better if it was all in one line, but they had it down the next line. So it's the LU decomposition over here that we're taking, and by using the LU decomposition, the idea is that solving for a linear system like this becomes a little bit easier. A lot easier? A little bit easier. So your solution is going to be the x vector, and that is negative 7 halves -2, and -1. Okay, that came from this. Questions? So,
so like the first row where you have 2, 1, and -2, and thing is you had +1, but then you had a -1 like right where you have x1 minus x2 minus x3 or minus 2 x3 or something like that.
so that should have been a positive?
Yeah.
Yep. So 2x1 plus x2, you're right, and then -2x3. So this is a positive.
And because then you'll end up with like a +2 with a -2, they're like canceling them out.
0, and then it becomes -3/2.
Yes.
All right. Thanks, Chris. -3/2. All right. Okay, so back solving, because it's a lower triangular or upper triangular, the back solving business is a lot easier to deal with, and so the solving for these systems is a lot easier to deal with. Okay? All right, so that's the use for it, or one use for it, but I want to go back to the idea of how to get the LU factorization to begin with. So let's do another example, and let's do that shortcut method instead of having to try to look for all those elementary matrices. So let's see if we can find another example. We can do number 4. I mean, the answer is right there, but should we do number 4 or should we make one up? It's never good to make something up, right? All right. Okay, so let's go through the steps of reducing to make this an upper triangular matrix in row echelon form, and then let's see, without identifying elementary matrices, let's see if we can just identify those multipliers that will make up our lower triangular matrix. So I'm going to keep the first row the same. Now my first step is to wipe out this 3. So I'm going to want to multiply this by -3/2. Well, this is where you want to be careful, right? There's a lot. We could swap rows and stuff like that. We're trying to stay away from swapping rows. And so the first thing I want to do is I want to multiply row 1 by no, I want to multiply row 1 by something by 3/2. What?
That's what I was trying to say.
What?
I was trying to say, why don't we just multiply the bottom one by 3 and add it to the middle one?
Because this is where you have to be careful about constructing your if you do it that way, then the elementary matrix will not work so well anymore,
Why?
because it might not be upper triangular.
How do you know when to not do that? If you want, like,
Well, if
you
you're
always have to start with the first row, is that it?
Yeah, so if your task is to get the LU decomposition, you always want to start with the first row. If you're doing this, multiply this by 3 and add it to the second row, then what's going to happen is that you're going to have an element here in your elementary matrix that's not going to be lower triangular anymore.
Yeah.
So if your point is then LU decomposition, you want to keep it lower triangular. So you always want to start from the top and then clear out the second and third lines in order. Okay? That's what gets you the unique LU decomposition. Yep. All right, so did that make sense? Okay. So if you're going to do row reduction to get the LU decomposition, you always want to start from the first row and then clear out the leading terms on the rows below it. Okay? So I'm going to look at this 2, and I'm going to see how I can knock off this 3. Negative 3 halves. So if I multiply this by a negative 3 halves, this is going to be a negative 3, and then this is going to be gone. So that's my first task, is to get my first row, and anything below this leading term, I want that to be 0.
Is that lower triangle or upper triangle still here?
The result here is going to be upper triangular,
And that's because it's going to have numbers in the top.
and the upper part. Yeah, so non-zero in the upper part means upper triangular. Non-zero in the lower part means lower triangular. Yeah.
So it's because we don't put it in reduced row echelon form that we just, for the sake of consistency, we always do it to get the same
Yes.
row echelon.
Yeah.
Okay.
Any more questions? So those are good questions. And if you understand those questions that you didn't ask, then that's good. If you didn't understand those questions, then now I want to deal with a negative 1. Yeah, well, we need to finish this row though. So 3 halves times negative 4, negative 3 halves times negative 4 is going to give me a positive 6, plus 1 is positive 5. Yeah, because we want our result here to be upper triangular. That's part of our answer is to get that upper triangular matrix.
So as long as that's 0, it doesn't matter what the other 2 are.
Well, if we want to give an answer of an upper triangular matrix, we still want those numbers.
When you were pointing out that upper triangle doesn't mean that the upper triangle part is non-zero, it just means that there's no requirement on it.
There's no requirement, but you still,
It could be non-zero.
yeah, they could be 0, it could be non-zero, but you still want to know what they are. Because you're going to give an answer of an upper triangular matrix, then they want to know what those numbers are, 0 or non-zero. All right, so this is 0 times 3 halves and 4, so that's just 4. How do I get rid of the second one down here? Or the third row? Positive 2, row 1, added to row 3. 1 half. Positive 1 half.
We only use the first row to do
And then for the next step, we're going to use the second row to wipe out the other one. So yeah, this is what Hal was saying. You got to be really careful with this. And the process has to be exact. It has to be from the top to the bottom. I didn't think about that because that's what I always do. But I suppose there's other ways. All right, so 1 half times 2 is 1. 1 minus 1 is 0. 1 half times negative 4 is negative 2. Negative 2 is 0, right? And then that's 0, so this is just going to be 2. So it looks like it's upper triangular already, right?
Then we don't have 3.
So we don't have 3, so that means this would just be 0. Okay, so this is your U matrix. This is the upper triangular matrix that you want. Now to construct your lower triangular matrix, this is unit lower triangular, by the way, so we know that the diagonal is going to be 1s. And we know that the upper part of that is going to be 0s. So we just need to figure out what goes in the lower part. And what goes in the lower part, and there's something with the R1 and R2. I think this is the row and the column or something like that, or column and the row. I don't know. So I have a negative 3/2 that I multiplied row 1 and added to row 2 with. And the opposite of negative 3/2 is positive 3/2. So we're going to take a look at this, change the sign, and that's going to go in that slot. That slot that you actually, the time when you got rid of that 0 right here. Or you made this into a 0. Next is this slot over here, which you were able to get rid of by multiplying it by 1/2. So instead now we're going to multiply by negative 1/2. And then this, we didn't do anything. This was already 0, so we'll just put 0 there. So lower triangular doesn't necessarily mean that every single one is non-zero. It just means there's no requirements for it being 0 and non-zero. So this is your lower triangular matrix. So A is equal to L times U. So these are your two matrices. When multiplied together is going to give you A. All right? Question? It shouldn't take more than 3 steps. For a 3 by 3 matrix, it should, since this is all you need to get rid of, 1, 2, 3, it should take 3 steps. Exactly, well, three steps or less to get that. Yeah. Okay? Is that looking okay so far? So this is an actual problem that has a solution. Here is the answer. 2, -4, 0, 5, 4, and 2 for the upper triangular part. And 1, 0, 0. This is a 3/2, 1, 0, and -1/2, 0, 1. So that's the same thing that we got. Okay? Now, what if for some reason, I don't know what the reason would be, but what if for some reason, should we do this now? All right, well, let's do another problem. Let's take a look at this particular matrix over here. And if we attempt to do what I was doing in that particular algorithm where it has to be really, it has a set algorithm, you have to do this exactly the way it is, which is we take the first row and we try to wipe out everything that's underneath. You see that we have a problem here? So our problem is that our first row and the first element in the first row is 0. Okay? So we can't reduce the way we did earlier. So what are we forced to do in this case? We were forced to switch. We were forced to swap exactly the thing that we were trying to avoid, right? Okay, so all right, let's swap it then. So I probably would like the third row up on top, right? So let's swap the third row and the first row. So now I can do what I need to do to get my LU decomposition, but we had an elementary matrix operation that we have to account for. So let's call this matrix B, and the question is, we need to identify an elementary row operation where we swap rows. So what is that elementary row operation matrix that we did? 0, 0, 1, 0, 1, 0, 1, 0, 0. So we swapped, if we take the identity matrix and you swap the first and third rows, this is really what happens. So so we can rewrite A as equal to E1 times B, right? Or is it E1 times A is equal to B? E1A is equal to B. Is it? So it turns out that E1 inverse is actually equal to E1. If we take a matrix and we swap row 1 and row 3, and then we take that same matrix and we swap row 1 and row 3 again, what do we get? We get back the original matrix, right? So that sounds like it's the inverse. Okay, good. Okay, good. So we can write this like E1A is equal to B, or we can write it as A is equal to E1B, right? Okay. So we would solve for this. We're out of time. And I would probably name E1 as something else. They call it P, because of a swap in a row is like a permutation, so they call it permutation. And then the transpose also, they call it PT, as in P transpose. So we'll have to come back to this next time. All right, so next time we'll talk about the PT-LU decomposition, which is introducing this idea of swapping it. And then we're going to do an LDU decomposition where there's going to be a diagonal matrix in between the lower and upper triangular. So we're going to talk about some decompositions.